All right. So, this is actually the second lecture, should have happened on Tuesday. Before I start, I want to answer a question, very interesting question which came up yesterday, that we have seen that a uniformly accelerating observer has a horizon. People too far from them, from the uniformly accelerating observer, cannot communicate with the accelerating observer. Now, according to the equivalence principle, this situation, the accelerating observer is equivalent to observer static in a uniform gravitational field. Static in a uniform gravitational field, will they see a horizon? So, yesterday I was not clear, but today I think I'm clear. The answer is yes, they will see a horizon for the following reason. If there is a uniform gravitational field, for you to be an inertial observer, you should be freely falling in it. If you fall freely in it, you are an inertial observer, then you will not see a horizon. But if you are staying put, despite the gravitational field, you are not falling, you are staying put, you are actually an accelerated observer. You see what I am saying? Sitting here on the earth, I am an accelerated observer. Of course, the field here is not uniform. The earth's gravitational field is not uniform. We are talking of the idealized case, staying put at one place in a uniform gravitational field. You are an accelerated observer. To describe any motion, you must use Rindler coordinates if you are doing it according to special relativity. And then the same reasoning applies. Such an observer will have a horizon and the equivalence principle is being obeyed. We can go into this in some detail with the maths if you like, but this is the answer. If you have anything you want to clarify regarding this, please we can discuss now. Yeah. Okay, so what we want to talk about today, comparing and contrasting gravitation and electrodynamics, similar at the non-relativistic level, but very different at the relativistic level, and we want to understand that in some detail. And tomorrow we'll start differential geometry, differential forms, connection one forms, etc. So let us compare Newton's law of gravitation with Coulomb's law of electrostatics. So Newton's law of gravitation tells us what is written here, the inverse force square law, minus sign because the force is attractive, and obeys this law proportional to product of the masses. The force can be written as minus the gradient of a potential, and for two particles separated by a distance r, this is the potential. The potential obeys the Poisson equation for a distribution of masses, and this is a special case of this. Okay, the force is attractive only. Gravitational force, as you know, is attractive only, it's not repulsive. In other words, there is only one kind of gravitational charge, that is mass. It has only one sign. Let's compare with Coulomb's law of electrostatics. There is a coupling constant, I think this is called what? Electric permeability, coefficient of electric permeability, if I remember correctly. Similar structure as gravity, but no minus sign because the force is attractive as well as repulsive. The force is still given as minus grad phi. The potential has a form similar to this. The equation corresponding to the Poisson equation also has the same form, but now there is a major difference. Electrostatics is attractive as well as repulsive, and electric charge comes in two signs. This is already very deep. We need to ask, looking into the future at unification issues, why is it that the gravitational charge, namely mass, comes with only one sign and electric charge comes with two signs? So maybe I take a couple of minutes dwelling little more into this issue, but if you want to, if you have any thoughts on this, do share. So this is a research question, unanswered. Could it be that I need to, for reasons that I'll come to, work with square root of m, not m, given mass m, maybe make it dimensionless by dividing it, say, by Planck mass. Square root, when I take, there are two signs, plus minus square root of m. This begins to look like electric charge. So is it that the correspondence between electric charge and mass is not electric charge versus mass, but electric charge versus square root of mass? When because if I take square of plus minus root m, I'll always get m with a positive sign. Yeah, you agree, no? So I want to, since I have been working at this for some time, I want to say why this is interesting, because it's not usually often talked of. So I want to try this, sharing the iPad, and see if I will succeed. Okay, hey, can you, yeah, you can see this, no? Huh? On Zoom also? Yeah, okay, something is working for a change. Okay, so we want to look at elementary particles, neutrino, electron, then up quark and down quark. These are the four elementary leptons, okay, and their antiparticles. Let us write down their electric charge ratios and mass ratios. Neutrino, leave out, it's a very complex business. Don't know whether it has a zero mass, so leave out the neutrino. What are the electric charge ratios? 3 to 1. Yeah, electric charge ratios are 3 to 1. The down quark is 1/3 of the electron's charge. The up quark is 2/3 of the electron charge, and the electron is 1. So 1, 2/3, 1/3 you can write, or you can write like this. Now what about the mass ratios? Within our experimentally allowed error bars, this is how it goes. 9, 4, 1. This is very interesting. So 1, 4, 9. Now you take the square root of this. Square root 1, 2, 3. So their electric charge ratios are 3 to 1. The square root mass ratios are 1 to 3. It's extremely puzzling. Am I to say this is a coincidence? Probably not. It's a hint that there is something deep going on here. Now what about plus and minus? I mean, where is that coming? Okay, so question? So here is the proposal that corresponding to every particle, there is its antiparticle, electron, positron, up quark, anti-up. Let me put a for anti-up, and down quark, A for anti-down. These fellows have the opposite sign of electric charge. So if this is, if electron is negative, minus, that you understand what I'm saying. The down quark has a negative charge. Let me say this: negative, positive, negative. Neutrino is 0, electrically neutral. And this is positive, negative, positive. Down quark is negative, the up quark is positive, electron is negative, positron is positive, anti-up is negative, anti-down is positive. What is the definition of an antiparticle? It has the same mass as the particle but opposite sign of electric charge. Yeah? But notice what we call particles Hand, okay, is there a question? Abhishek. But if we do it the same charge and mass ratio with protons and up and down quarks, no, please leave out protons. Protons are extremely complex objects. They are not fundamental states. They are not fundamental particles. They are made up and down quarks. Most of the mass of the proton are derived from the strong force field. The binding energy is where the proton's mass comes from. You are right, there is no 3-to-1 ratio there, but proton is not an elementary particle. Proton is a composite of up and down quarks. Okay? Right. So, the mass remains the same, but the sign of the, one more chat. Okay, the mass remains the same, but the sign of the electric charge changes. So what I am proposing, let us look at square root mass. I will assign plus sign of square root mass to the particles, minus sign of square root mass to the antiparticles. Do you see what I am saying? When I square it, plus root m and minus root m will have the same, not plus here, not plus, minus. Not plus. Minus. What we call particles have plus root m, what we call antiparticles have minus root m, so that their mass is same. Now, the electric charge ratio is 3-to-1, square root mass ratio is 1-to-3. This is also interesting because if I asked you, can you tell me what is the difference in the definition of matter and antimatter? Let us ask this question. How is matter defined? How is antimatter defined? In some nice dynamical way. I can't say that for every particle there is an antiparticle. And I cannot use electric charge to distinguish matter and antimatter. Why? Because some things that I call matter have plus charges and some things that I call matter have minus charges. So the proposal is, please let us, maybe there is a new dynamical field which we actually see in our work, which we call, which is a U1 field, which couples with square root of mass. It is like electromagnetism, but instead of coupling with electric charge, it couples with square root of mass, and we call it dark electromagnetism. Okay, so matter is that which has positive sign of square root of mass, antimatter is that which has negative sign of square root of mass. Maybe there is a new field in, this is research, ongoing research only, maybe there is a new field in nature which couples to, so we come back to this question, why is mass always, why is gravity only attractive? Maybe there is something to do with another force which is having plus and minus root m as its charge, which is the analog of electric charge, and maybe there is something like a Coulomb force, like a dark electromagnetism, which is the analog of You want to say something here? Okay, let's go on. So this is the comparison between gravity, electrostatics and Newtonian gravitation. Let's move on. Okay, what about magnetostatics? What is magnetostatics? Steady currents, currents that are not changing with time, steady currents produce magnetic field. A uniformly moving charge is a uniform current, it produces a magnetic field. So what will happen? There are no time varying E and electric and magnetic fields. The equations are Maxwell's equations, relevant ones reduced to divergence of B is 0, curl of B is mu naught J, is the so-called coefficient of magnetic permeability. Now I can simplify, I can write this in terms of a potential. I take B as curl of A. So I have curl of A that will give me a Laplacian term and a divergence of a term. The divergence of a term, I choose a gauge to set divergence of a to 0. This is how you can calculate the vector potential due to a current. And right. Interesting to note that magnetic fields do not fall off as inverse square of distance, but there are no magnetic monopoles. But there is a approximation to Maxwell electrodynamics, which we call magnetostatics. So, and also Maxwell's equations are invariant, are Lorentz invariant, but to do that, to make sure that Maxwell's equations are Lorentz invariant, electric and magnetic fields must transform into each other. They are part of the electromagnetic field tensor. Now comes up a very interesting question, which I don't think I have a clear answer to. I've been thinking about this. Why is there no analog of magnetostatics in Newtonian gravitation? Is magnetic field a purely relativistic effect? So it's interesting to spend a few minutes, and I would like some feedback from you, because you have also studied, you know probably electrodynamics better than I do. You have studied it recently. This is, I think, a very interesting question. There is no speed of light appearing in magnetostatic equations. Speed of light will appear if you have mu naught and epsilon naught both. Epsilon naught goes with the electric field, mu naught goes with the magnetic field, and speed of light square, I think, is 1 over mu naught a naught. It's a product of mu naught and a naught. So in this sense, magnetostatics is a non-relativistic effect. It has essentially the same status as the Coulomb's law for electrostatics. Then what is happening? Why is Newtonian gravitation not showing a magnetostatic analog? I have a uniformly moving uniformly moving masses along, let's say, and you understand, it has momentum. You have a bead of masses, the whole bead is moving. It still produces only the Newtonian gravitational field. Doesn't matter whether it's moving or not. It doesn't produce any additional analog of the magnetic field. Do you have some thoughts on this? I want to discuss this because I'm not 100% clear. I had an explanation, but I don't know if that is correct. Anybody, any thoughts? Let's discuss. Do you see there's a problem? You see there's something to think about, Snail? Yeah. So one answer I thought of is that it has to do with the equivalence. Yeah.
Apart from it is so nice, why should we expect both should be, in the same footing?
Where can I just see the chat? We have a relativistic energy relation. Is there any expansion? Okay, please take this up in the end, ask again, huh? Yeah, say that.
So why should we expect that there should be analogy between gravity and...
No, we are trying to understand. Normal picture is that at the non-relativistic level, they are the same. Now, it's Coulomb's law and Newtonian gravitation are at par. So I'm asking a question. You are right. Why should it be? But then we are asking an answer. Why should they be different? Yeah. So one thing I thought of, I don't know if it's correct, is the equivalence principle. You move with that mass, then there's no gravitational field because you are in the rest frame. The principle of equivalence would tell you if there is no curvature in the rest frame, there should be no curvature in any other frame also due to this motion. But that is one possible answer. I don't know if it is the correct answer. It is still something for us to think about.
Why wouldn't there be gravity if you're moving with the mass?
Go to the rest frame.
Still it will attract towards it.
No, gravity will be there. Coulomb gravity will be there, but there is no, there can't be a magnetic analog, no?
That is not there.
Yeah, the Coulomb field will be there. The Newtonian gravity of a moving mass current is the same as that of the mass not moving. That's the Coulomb, that's the 1 by r square, or if it's a wire, then it will be 1 by r, doesn't matter. You are right.
You're giving some resolution,
That part was not clear, is it? So what I am saying is equivalence principle. Go to the rest frame of the moving mass current. Now there is no current, so there will be no magnetic gravitational field. And so the curvature corresponding to the magnetic...
But that is true of charges too. If you're moving with the charges...
Oh no, we have to be very careful, because you go to the rest frame of the moving charge, because of length contractions, things will happen. Now let's see, what will happen? The E and B will transform, you see. There will be no B, but there will be a E, which should be different from when it was not moving.
The density will increase.
Yeah, the E field will change. The electric field will change, unlike in the gravitational field. The gravitational field would not change.
It should also have the same thing. There should be length contraction and the density of matter.
I think, I don't know, because you have to obey the equivalence principle.
So what is actually an action at a distance?
Action at a distance is, if the sun moves, its gravitational field at the location of the earth the change is immediately felt here. Sun is having a gravitational field of the earth. If its position changes, it will instantly affect the earth. That is action at a distance.
So why the electromagnetism is not action?
Yeah, because it's a relativistic theory. It's a relativistic theory.
You're comparing it to Newtonian gravity.
Now, so this is subtle now. Even in the, if you suppose I write Coulomb's law in the non-relativistic limit, I have an electron and a proton. I change the position of the proton. If I am obeying Maxwell's electrodynamics, there will be a delayed effect.
No, electromagnetism, that is fine. But you said something about the sun, if it moves...
Yeah, in the Newtonian gravity. Yeah, that's what you were asking. Newtonian gravity is action at a distance. More questions? Spinning the star may be generating an equivalent vortex. Yeah, these are good points being raised. We'll come to the generation of the. But what I'm asking is, at the non-relativistic level, why is there a difference? We agree there's a difference at the non-relativistic level. There is no magnetic gravitational field, and we are trying to understand what is the reason for that. So I leave it for further discussion. I don't know whether the equivalence principle part is the explanation. Okay, all right. So this is one open thing. But what if I try to make a relativistic theory of gravitation which is like electrodynamics? Forget, let's say there is magnetostatics, there is E and B. Electrodynamics is a relativistic theory. I want to make a relativistic gravitation. Newton's law of gravitation is not relativistic. I want to make a relativistic theory. I want to make this relativistic. I cannot just do it with a scalar field because I have to make a current. Yeah, at least moving masses have to take in. So at least I should do is have a vector field. So what are we doing? Trying to make a vector field theory of gravitation. We know that is not possible. It's a second rank tensor theory. The metric is the potential for the gravitational field, and it's a second rank tensor. The potential in electromagnetism is a vector, it's a 4 vector. So let's see why we cannot have vector theory of gravitation. So this you remember, of course, just quick review. The field tensor satisfies two source-free Maxwell's equation. This definition of dual, where this is the unit antisymmetric tensor, we will use later. These are Maxwell's equations with sources, and the force, the Lorentz force law is here. So I think I have to again go to chat. Is it because of frozen? How should I deal with the chat questions in the end, or? Yeah, I'm reading. If there is something immediately that I think it should be responded to, I will do my best. So the left side is clear. Now on the right hand side, why can we not have a Maxwell-like generalization of Newtonian gravitation? So I want to write down a 4-vector potential like this and ask what will be the source. I make a source which consists of mass density and a current corresponding to moving masses. Okay? So this I have discussed a little bit earlier also. Now I go through it once again with some care. The principal answer is that mass is not a scalar, unlike an electric charge. Mass is same as energy, E equals mc square. But this mass energy is a part of a 4 momentum vector, energy momentum vector, which satisfies E square minus P square equals m square. So if suppose this was possible, now you go to a moving frame, the mass is going to not remain a scalar. It will transform as the 0th component of a energy momentum 4 vector. You see what I am saying? Suppose this is, you wrote mvi. You want to write this current as mass times velocity. Go to a moving frame. Velocity I know how to transform. It's a 4 vector. But I have to transform mass also. I should write mass as P0, where Pi, let's say, is a energy momentum 4 vector. You see what I am saying? Mass is P0, P0 ui. Transform it, it becomes something like Pi uj or u or Pi pj. Already it's a second rank tensor. You see what I am saying? If your source current is a second rank tensor, your fundamental field cannot be a vector potential. Please ask me if this is not clear. So the reason why gravitation cannot be a vector theory is because, unlike the electric charge, mass is not a scalar quantity, it is frame dependent. Then there are other reasons related to do with experiment, etc. Mass is the 0th component of 4 momentum. So we need current of 4 momentum. This is called a current of current. Momentum already is a current, and as a source, you need, that's why you see in the energy momentum tensor, you don't just have energy momentum density, energy momentum contributing. You have things like pressure also and stresses also, that they are coming because of this current of current, Pi, Pj, which it has terms like P squared, kinetic energy, that is what gives rise to the pressure. So if it is not clear, please stop me and ask. We will need a second rank tensor as the source, and hence the potential also should be second rank. Why? Because what is the field equation? It's the second derivative of g mu nu is proportional to t mu nu. The Riemann tensor second derivative of g mu nu. So if the right hand side has a second rank tensor, the left hand side also should be derivatives of a second rank tensor. And there are other ways we can argue, because gravity, because of equivalence principle, gravity is geometry of space-time, geometry of space-time. If it is Riemannian, it is described by the metric. That is another, and again, if you have metric, you should have energy momentum tensor. So somehow all these things, the equivalence principle and mass not being a scalar, probably these things are related to each other. Any questions?
AMU, there is a psi in there for defined with the open potential.
Huh?
There is a psi in minus A. Is there?
Yeah, I think the A upper, A lower. When you this A lower is the covariant version. If here your metric is signature plus minus minus minus, A mu upper is phi A, A mu lower is phi minus A because of the Minkowski metric.
Then the size changes also change. Minus phi, A mu upper mu is equal to minus phi and A.
Psi or phi?
A of mu.
Upper, the zeroth component is phi. That will not change sign because your metric here is eta mu nu is diagonal plus 1 minus 1 minus 1 minus 1. So A mu lower is eta mu nu, A mu upper. So the zeroth component will not change sign. Or if you are using another signature, zeroth component will change sign, the other one will not. Yeah? Okay, now it gets more interesting. All right, there is no magnetostatics in gravitation, but there still is a Maxwell-like approximation to Einstein equations, which will be taught, I think, by Patrick later. But just for fun, I want to give you a glimpse, at least show you the equations. So Einstein equations, second rank equations, do have an approximation which we call gravito-magnetism, where Maxwell equations and Einstein equations actually look alike. So we are saying in the non-relativistic limit, there is a difference. There is no magnetostatics in gravity. But if you go little beyond non-relativistic, the next order terms in a V by C expansion if you keep, then you can make an analogy. So this is just a glimpse of what will come. Take the metric, write it as a perturbation of the Minkowski matrix. H mu nu is very small compared to 1. Make a transformation to a new gauge. H bar mu nu equals H mu nu minus half H. Make this transformation. Use the so-called Lorentz gauge condition, and in this approximation, I am just giving you the results. Einstein equations reduced to these linear equations which look like Maxwell equations, except of course they are second rank tensor H mu nu. But in the weak fields are weak, matter sources are moving slowly, you can approximate your energy momentum tensor to have just these components T00, T0I, mass and its current, and that is rho, J times rho V, rho is mass density. Define H00 as related to phi g like this, H0I, this is a definition. Define the gravitational analog of the vector potential spatial part like this. Define gravitational analog of the electric field in this way, gravitational analog of the magnetic field in this way, using these components of the metric. These are all coming from the metric now. Then Einstein equations in this approximation are Maxwell-like. Okay, divergence of Eg is minus 4 pi g rho. Curl of Bg has this current term which is due to the mass, then a term due to varying electric field. Divergence of Bg is still 0. No gravitational analog of magnetic monopole. and then this last equation. Okay, so this is more than Coulomb's law. Coulomb's law would be just the, sorry, more than Newton's law of gravitation. Newton's law of gravitation just be the first equation, the other three are not present. Whereas in magnetostatics, you have the first equation, sorry, in the non-relativistic limit of electrodynamics, you have the first equation and you have the second equation with the J term. You don't have the time dependent electric field, but you have two equations, whereas in general relativity, Newtonian limit, you have only the first equation, and that's why I think there is something to be answered here. Yeah, I think that needs some attention. So this is gravito-magnetism, and these are observed effects. A rotating mass like the Earth, for example, generates a gravito-magnetic field. This question was asked in the chat, and it produces effects like so-called frame dragging, where the inertial frame is dragged, the lens-steering precession of gyroscopes, which is confirmed by experiment, and hopefully this will be covered in the forthcoming tutorials and also in Patrick's lectures. Right. But what is important to remember is that Maxwell's equations are exact for all speeds, right? It's not as if they are true only for low speeds, they are exact. But the Maxwell-like approximation to Einstein equations requires a slow-moving expansion. Very slow, the leading order would be just Newtonian gravitation. At the next order, you will get the analog of magnetostatics. But if you go to higher velocities, this approximation breaks down. Additional effects will come in, which have to do purely with general relativity being a nonlinear theory. By the way, interesting, this is a linear theory, right? In the Maxwell-like approximation, general relativity becomes linear, but the theory is intrinsically nonlinear, and at high speeds there will be, of course, be a departure from the Maxwell analog. Okay. Any questions, please? Yeah.
So, how are the nature of the sources? So, these are the equations. Linearization means far away from the source.
This is okay. Yes. Fields should be weak. H mu nu should be less than. You have to be in a region where H mu nu is weak. So, essentially, yes, far away from the, or the source is weak. No, Earth is a weak. So, what decides weak or strong? Phi by c square. Look at the potential in units of c square. If phi by c square is much less than 1, then the source is weak. Along with that, V by c should be much less than 1. Weak field, slow moving. You can have weak field, fast moving, for example. That would give you gravitational waves. Their H mu nu is much less than 1, but the sources are relativistic. So, weak field, slow moving is what is used here.
So, these are essentially gravitational waves?
No. Weak field, slow moving. Gravitational, weak field, fast moving. You see the difference? There are two approximations happening. Phi by c square should be much less than 1. V by c should be much less than 1. In the gravitational waves case, the second one is not there. Only phi by c square much less. Yeah? Okay. Right. So, since today's talk is about comparing gravity and electrodynamics, we are going through various aspects, and this you are familiar with by now. The so-called the weak equivalence principle just says that all objects fall at the same rate in a gravitational field regardless of their mass and internal composition. The gravitational charge, or m gravitational, is equal to m inertial. This is the weak equivalence principle. It tells us how test particles behave in gravity, but it does not explain what gravity is. By itself, it is not saying that gravity is the curvature of space-time. That conclusion comes from the strong equivalence principle because of the Einstein elevator experiment. You are inside a sealed elevator. Can you tell if the force you feel is due to gravity or because the elevator is accelerating in space? If not, then locally acceleration and gravity are indistinguishable. The laws of physics must be the same in a uniformly accelerated frame and in a gravitational field. Obviously, this is not true for electrodynamics. The analog here is electric charge. Electric charge is not, E by M ratio for different objects is different. It is not universal. The ratio of electric charge to mass changes from particle to particle. So, because of that, the electrodynamics does not obey the equivalence principle. Okay? That, of course, as we have been talking, it does not mean that electrodynamics cannot be a geometry. It cannot be a geometry of space-time, but it can be a geometry of some other internal, so-called internal space, which we will talk about, the so-called fiber space. Yeah. Okay. So, because of the strong equivalence principle, gravity is indistinguishable locally from an accelerating frame, a non-inertial frame. In a non-inertial frame, space-time geometry is non-Euclidean. Hence, gravity is equal to space-time curvature. We need to understand this carefully. So, what are we saying? In a non-inertial frame, space-time geometry is non-Euclidean. This statement is strictly not fully correct. Yesterday we saw the accelerating frame. It's a non-inertial frame. The metric is not Minkowski, but the geometry is still Euclidean, right? Because we are in flat space-time. So, just going to a non-inertial frame does not imply non-Euclidean geometry. Something more is needed, so that you know it, of course, already, but let us review that. Why is gravitation the curvature of space-time? In an inertial frame, where laws of special relativity are obeyed, free particle motion is along the path of a shortest length in space-time. This is okay, right? Now transform to a non-inertial frame which has a non-trivial metric, like we saw yesterday for the Rinlove frame. Free particle motion is still along the shortest path. The particle is falling free, a free particle is going in space-time, and I am observing it from an inertial frame, and then I start accelerating. Nothing is going to happen to that particle. It will still obey shortest path motion, but the description of the line element, distance between space-time elements, has changed. ds square now has a non-trivial metric, like we saw yesterday, right? The Rinler metric is not trivial. It's not the Minkowski metric. So there you will write the line element like this, but the free particle is still obeying a geodesic motion. That motion is now described by the geodesic. Has this been covered in the lectures so far? Geodesic equation? Not yet, is it? Tutors also know? Okay, so please, you have probably seen this before. In a non-inertial frame, geodesic motion is given by this equation, irrespective of whether the geometry is non-Euclidean. So right now all we are saying is, if you are in an inertial frame, the Christopher-Sten symbols are 0, and you will get d2xi by ds square is 0. If you are in a non-inertial frame, the gammas are non-zero, and you will get this kind of equation of motion. Right. So, but by itself, this does not imply non-Euclidean geometry. in a Rindler frame also I will get non-trivial gamma, non-zero gammas, and you will write an equation like this. By itself, the gammas don't imply curvature. That's all I'm saying. A non-zero gamma does not by itself necessarily imply curvature. What does the strong equivalence principle say? Motion in a gravitational field also geodesic, and it is determined by the metric which is equal to the gravitational potential. Okay? That is, this is a statement in a local, if you have a, let's see that again. Locally, acceleration and gravity are indistinguishable. Okay? Laws of physics must be the same in a uniform, blah blah. Okay. By itself, this does not imply that space-time has become curved. I have a gravitational field. I can equivalently view from accelerating frame. Geodesic motion still is described by like this. But if the gravitational field is uniform everywhere, like we saw yesterday, and a non-inertial uniformly accelerating frame is equivalent to a uniform gravitational field, the uniform gravitational field is not non-Euclidean. Okay? Just by going to a non-inertial frame equivalent to gravity does not produce space-time curvature. What is needed is that the non-inertial frame equivalent to gravity is different at different places. Suppose you have the earth here and two elevators are falling towards the earth. They will not be parallel, no? They will be both falling towards the center of the earth. The two elevators will start coming closer and closer to each other. And to go to the equivalent non-inertial accelerating frame, you have to use two different frames. If you need different frames as you compare neighboring points, that is when geometry is non-Euclidean, and that information is captured in this geodesic deviation equation. Namely, if there are two geodesics nearby and xi is the vector telling, I think maybe we need to draw this, xi is the vector telling, so I am saying if you are in a uniform gravitational field, the gravitational field is always pointing in the same direction. Here there is no curvature. This is like the Rindler case yesterday. But if you are observing the gravitational field of the earth, these geodesics, the paths of shortest length, are converging, and the xi mu vector, which measures the distance between two neighboring geodesics, is changing. Here xi mu is not changing, it's a constant. If you write xi mu as the distance between two geodesics here, in the uniform case it is not changing, here it is changing. And what decides whether the geometry is non-Euclidean is whether this separation vector xi mu is changing as you go from one location in the gravitational field to another. Yes, okay, I think I need to say something. Any questions here, please?
So that xi mu is the separation vector.
Yeah.
So
U mu is the tangent vector along the geodesic. Xi mu is the separation vector. Yeah, yeah.
and whenever we are talking about the geodesic deviation equation,
Yeah.
we are essentially talking about the differential equation in xi mu. Please show that.
Yeah, yes.
That is the second order thing.
Yes. Right.
So as and when the geodesics are converging, so what will be the fate of this equation?
Yeah. It is proportional to the Riemann tensor. The right hand side, R mu nu rho sigma is the Riemann tensor, which is made up of Christoffel symbols and their derivatives. If the Riemann tensor is non-zero, the geodesics will come closer. Or conversely, if the geodesics are coming closer, the Riemann tensor is non-zero. Yeah, so I should say something more clearly. Why is motion in a gravitational field also geodesic? Why in a gravitational field motion is along the shortest paths? Let's see. So where does that come from? You go to a non-inertial frame, the geometry becomes non-trivial. It has a G mu in it. But a non-inertial frame is equivalent to an inertial frame with gravitation, which means in gravitation also, what I want to say, gravitation also the motion has to be described in the same way. The way that you describe motion, free particle motion in a non-inertial frame has to be the same that you describe motion in gravity. That's because of the equivalence principle. I hope you see that, yeah? Because I can't locally distinguish gravity from a non-inertial frame, the way I describe free particle motion in a non-inertial frame, that is this, I must do it the same way in gravity. In the presence of a gravitational field, the motion of a particle will obey this equation. But just because this equation is being obeyed does not imply that there is curvature. Gravitation is equal to curvature only when gravitation is varying from place to place. Yeah. So why I emphasize this again and again, this equation is true always in non-inertial frames, but non-inertial frames by themselves don't imply curvature. Curvature is the effect which involves gammas and their derivatives, not just gammas. Gammas should be changing from place to place. In other words, the second derivative of the metric should be non-zero, which is what it is. The Riemann tensor second derivative of the metric. If only the first derivatives are zero, then you will have zero gammas, with derivatives of gammas will be zero and the curvatures will be zero. Okay?
So I mean, non-Euclidean geometry is characterized by rather the geodesic deviation equation than the geodesic.
Absolutely, yes, yes. That's very well put. That was what I was trying to say, but not able to say. Gammas and geodesic equation don't decide non-Euclidean nature. It's the curvature which decides the. And curvature is gammas and their derivatives. Okay, any more? Okay, now again, so since this is a comparison talk, I also wanted to say something about the role of the Lorentz group in general relativity. The gauge group in electrodynamics is U1. The set of general coordinate transformations in general relativity, that group is diff M, but still the Lorentz group SO13 has a role because of the equivalence principle. Locally in a gravitational field, locally when I free fall, the laws are that of special relativity. So the local Lorentz transformations will obey this, satisfy this group. What is SO13? The group of 4 by 4 matrices orthogonal with determinant +1, which leave the Minkowski line element unchanged. That's what it is, the group of Lorentz transformation. And there's a technical statement that this can also be written in terms of these special linear 2 by 2 matrices with complex entries. The determinant 1 and determinant -1 cases of SO13 both correspond to the so-called SL2C. In special relativity, SO13 describes the global symmetry of flat spacetime. In GR, this is a local symmetry. Lorentz invariance is local. In general relativity, the Lorentz group acts as the local symmetry group of the tangent space at each point in spacetime. It governs how vectors, tensors, and spinors transform under changes of local inertial fields. Remember the tetrad, for example, you can make Lorentz transformations on the tetrad, and that will be determined by this Lorentz group. The local symmetry of tangent space, what does that mean? At any point P on a smooth curved manifold M, the tangent space Tp of M is a flat Minkowski. This I think Patrick talked about yesterday. Yeah. The Lorentz group SO13 is the group of linear transformations on the tangent space that preserve the Minkowski metric. Lambda here is a Lorentz transformation. Curvature breaks global Lorentz invariance but preserves local Lorentz. I brought this up just to compare U1 of electrodynamics with the Lorentz group. Yeah. Okay. Now let's bring in tetrads. What is a tetrad, also known as a Vierbian, and what does it have to do with Lorentz symmetry? A frame field, also called a tetrad or a Vierbian, is a set of 4 pointwise orthonormal vector fields. I think I defined a tetrad earlier. So the E A mu is a tetrad. There are 4 vectors. A labels a vector, A equals 1, 2, 3, 4 or 0, 1, 2, 3. So there are 4 vectors. Mu labels the coordinate, the space-time coordinates of each of the vectors. There are 4 such vectors. 1 is time-like, 3 are space-like, defined on a Lorentzian, local manifold, local Lorentz, or on the tangent space if you want. G mu x, the metric, the space-time metric is related to the tetrad by this. So we think of the tetrad one way as the square root of the metric, but more important that it is defined on a local Lorentz frame. Vierbians relate coordinate basis to a local Lorentz frame. Yeah, right. So G mu is on the coordinate basis. It is defined as a function of coordinates, and you can make a transformation from the coordinate basis to the local Lorentz frame. Meaning if you free fall, you can work with tetrads, and that is related to the metric like this. The Lorentz group acts on internal indices A, B. It does not act on the space-time coordinates. The local Lorentz group is a gauge symmetry, acts pointwise on tangent space. Essential for coupling gravity to spin half fields such as the Dirac field. The structured group of the tangent, I will come to this more. The structure group of the tangent bundle over the manifold is this Lorentz group SO13. So U1 is the structure group of electrodynamics on the fiber, which will come to next. The analog of that locally is SO13. Okay, any question? Yeah, so now moving toward tomorrow's lecture, moving towards the differential geometry. If you want a common language for gravitation and gauge theories, it is the language of fiber bundles, and let's start by having some basic idea of what it is. A fiber bundle is a mathematical structure that looks like a collection of fibers attached to every point of a base space. Base space is the space in which you are moving around. Let's say space-time or the Earth's surface. Earth's surface could be my base space. Fiber is what is attached to each point in the base space. For example, a little object like a string, a vector, or a donut, like depending on context. So it's another manifold which you construct on the base manifold at every point. At every point of the base manifold, there is a new manifold, that's the fiber. Fiber bundle, the whole collection of fibers, one at each point of the base space, is called a fiber bundle. A fiber question. Oh, a fiber bundle is like a field of objects smoothly distributed over some space. Yeah. Example: at each point on Earth, the base space, attach a flagpole. That's a fiber. Collection of flagpoles along with the base space is a fiber bundle. Bundles can twist. This is very interesting. So locally the structure is B cross F, base cross fiber. Every point it is B cross F. But a non-trivial fiber bundle is where globally it is not B cross F. You get some idea? So this Mobius strip is a very good, nice example. You've heard of it. Suppose you are on standing by the side of a round table with a, let's say, a pencil or pen, let this be a long stick, where the two ends, let's say, are distinguishable. Upper end is the pencil tip, lower end, let's say, is the eraser. Go around the table like this and come back. If you come back without doing anything to the pencil, you have a trivial bundle with a B cross F structure is global. Yeah, it's all this is a fiber bundle. You made a fiber bundle by going around the table. The boundary of the table is the base space, and this pencil going around is a set of fibers. Now do one thing. Now make it more. How to make the Mobius strip? As you go around, start tilting it. Come here, tilt more. At some stage, you invert the tip. The tip comes to the bottom, and then what happens? This is a non-trivial bundle. You cannot write it as B cross F everywhere because the F has changed. Yes, that's what the definition of a Mobius strip is. A little more formally, a fiber bundle consists of a total space E, a base space B, a typical fiber F, and a projection map pi from E to B. From the total space E to the base space B, there is a projection. You project as if you are then ignoring the fiber. From E cross B, you can project to B. At each point, little b belonging to the base space, the pre-image pi inverse B is the fiber over B. Yeah? Pi maps from E to B, pi inverse B maps from B to the fiber over B. In a tangent bundle, the tangent space is the fiber over the base space. So this is quite evident, yeah, right? And this is a vector space. So such a bundle where the fiber is a vector space is called a vector bundle. So there are different kinds of fiber bundles. A vector bundle is one where the fiber space is a vector space. And that is where it is different from electrodynamics. The structured group of the tangent bundle at every point of the base manifold, the tangent space is a vector space on which the basis can be chosen. This is for space-time. Transformations of this basis, which say preserve the Minkowski line element, form a group, the structure group that I have already said. For space-time, it is the Lorentz group SO13. So I think electrodynamics is next. Yeah, I will not. Okay, still talking about the tangent bundle of space-time, and whose structure group is SO13. How does the structure group relate different fibers across the base? This is very important. These fibers have something to do with each other. What is the role of the structure group? The structure group tells how to transition from one fiber, one local trivialization to the next fiber. That is, how are fibers over overlapping regions related or glued together? Yeah, you'll see this in this example. Imagine a manifold M, base manifold M, covered by overlapping coordinate patches U alpha. So you're describing the fiber space in two ways maybe. Once you are using a coordinate patch u alpha, and in an overlapping region you may be using coordinates u alpha and u beta. Over each coordinate patch there is a product space u alpha cross f. Okay? Need to glue the fibers in the overlap u alpha intersection u beta. For example, basis del by del x mu in u alpha and basis del by del x prime mu in u beta. The change of basis del x mu by del x prime mu belongs to the structure group. So let me slow down, we have enough time. You can use different coordinate patches, right? I can decide to use this atlases, and this Patrick has talked of, I think, already, right? You can use different coordinate systems at the same place. How those coordinate systems have to be related to each other in some way, and the change of basis will be given by this Jacobian. These transformations must belong to the structure group. Do you get some sense? The structure group is defined on every fiber on the tangent space, but it has more role than that. It is what tells you how you will transform from one coordinate system to another. Does this make sense? No? Okay, we will come back to it. We try to say it nicely. I think structure group on one fiber we understand, yeah? It is the group, what is acting on the tangent space. But if you have tangent space here, I use some coordinate system here which I extend there. Over there I start using some other coordinate system. But these coordinate systems will have to have some relation with each other to obey some good mathematical properties. The structure group is SO31 here, SO31 there, but you're using different patches. You can only make those transformations where the transformation function shown here has transformations which belong to the structure group. That's what I'm trying to say. Maybe I'm not saying it properly, nicely enough. We can try to digest it. Okay, so this is same as what I just said. I can skip it. Okay. What is the case of electrodynamics? The fiber space is now not a vector space. It is this so-called Lie group, U1, which I had defined earlier. Let's go through that. The base space is still the spacetime manifold M. Types of fiber bundles. A fiber bundle is called a principal bundle if the fiber is a Lie group. It's called a vector bundle if the fiber is a vector space. The tangent bundle is a special case of a vector bundle. In electrodynamics, the total space is a principal bundle E over M such that the fiber over each point x belonging to M is a copy of the gauge group U1. Fiber at x is an element of U1. What is U1? The group of complex numbers with unit magnitude, e to the I theta, where theta belongs to the interval 0 to 2 pi. This is the fiber for electrodynamics. Unlike for space-time, the fiber is a vector space, and this is the structure group on the fiber is U1. For the matter particle described by the state psi, the associated vector bundle is the complex line bundle C. The group U1 acts as psi to the e to the I theta x. Psi is a complex function, complex number. Psi is the set of complex numbers forms the bundle C to which the matter particle state belongs. So there's a fiber for the Lie group. Hopefully it will become clearer when I have introduced the gauge field. The group U1 acts on the complex line bundle in this way. The electromagnetic field arises from requiring invariance of physics under such a gauge transformation. So, gauge transformations belong to the group U1, and we require that under such gauge transformation my field equations should not change. Yeah, please ask me something because I don't know how nicely it is going.
These states, like the matter states psi,
Hmm?
they belong to the complex line bundle.
Yes, yes. For the fermion, I have a separate bundle, which would also in general be a vector bundle, but in the simplest case, it is this so-called line bundle. It's a special case of a vector bundle. The fermionic state belongs to this its own bundle, the complex line bundle. The gauge field is what makes the gauge field is what is required to retain gauge invariance. What is the action of this group U1? The fiber space is just this group U1. It's a group of elements of group of these unit norm complex numbers. These elements of U1 are acting on the state belonging to the line bundle. If under such changes the field equations should remain unchanged, I must bring in the electromagnetic field as a connection, okay, which makes sure that this action of U1 does not spoil the form of the equations. So let's see, are we under gauge transformations belonging to U1, if I require invariance of physics, I need to introduce a gauge field, the vector potential, which will then be the connection. That's the connection corresponding to the gauge group U1. We'll do that in the next slide. I hope you get some hang of what is. We can also discuss more in the evening if you like. So now I get something from my first lecture. The electromagnetic vector potential and the field tensor belong to Maxwell equation. These field equations are invariant under gauge transformations belonging to the gauge group U1. Consider a complex scalar field with U1 symmetry. This I described just now. U1 gauge transformations are acting on the matter field psi. Under this transformation, del mu of psi doesn't transform like the gauge transformation itself, picks up an additional term, del mu theta of psi, where if theta is space-time dependent. We don't like this. That's why we introduced the gauge field assumed to transform like this under the gauge transformation, and we define a covariant derivative d mu of psi by this relation, ordinary derivative of psi plus I e a mu, where a mu transforms like this. Now under a gauge transformation, d mu of psi transforms nicely, yeah, because the change coming because of A will change under a gauge transformation, psi will change under a gauge transformation, and these two, the changes in del mu psi under a gauge transformation will be cancelled by the changes in A mu under a gauge transformation, and this will hold. So why is the gauge field A being brought in? Because I want derivatives also to transform the same way as psi does under the gauge transform. So This object now, A is the connection. Connection is with what preserves derivatives under a gauge transformation. Okay? Gauge in all this last. So this. So what is happening? The fiber is the group U1. Elements of U1 are acting on psi, but they spoil the gauge transformation of del mu psi. So I bring in A mu to preserve this differentiation by defining this new derivative. So I say A mu, the gravitation, the electromagnetic vector potential, is a U1 valued connection one form. That's the language. If you don't want to call it one form, call it connection, U1 valued connection. So this is why we call the electromagnetic vector potential a connection, because it preserves the derivative under transformation. Anything you want to ask here?
Can you repeat what is a connection in this context?
A connection is what you need to make sure that this does not happen. The derivative transforms the same way under a gauge transformation as the state itself does. Yeah? Connections are needed to, or what we call also parallel transport. We haven't used that language, we'll come to that. Do you get the idea? So fiber space U1, connection A mu introduced to, for the reason that, so it's a U1 valued connection because it preserves field equations under U1 gauge transformations of the state. So identical thing will be done on the tangent space. When you take a vector from one point to another, the same kind of problem will happen. You transform, you acted on, make a derivative of a vector after such a transformation, you will have these additional terms coming in. So the gammas come here. The Christoffel symbols are brought in to make sure that this does not happen in the space-time case. So this has not yet been done, no? So it will come. So so this is where you see the similarity that preserving derivatives under gauge transformations is analogous to preserving derivatives under space-time coordinate transformations. I hope you get some hang of it. Can be said better. Okay, so I want to take this opportunity, since there are still 10 minutes. So I think one of you asked this, I don't know, someone asked this question. Why do we call the field tensor curvature? The connection, we have some idea. Why do I call the electromagnetic vector potential connection? Because of this reason. And then we keep saying that the antisymmetric derivative of the connection of the vector potential is the curvature, the field tensor. Why is the field tensor curvature? I think you asked me that, yeah, like that. So I give some glimpse. So what this is very much like what happens to the Riemann tensor. Under a displacement, we are in space-time, under a displacement delta x mu from a point x mu, a question. In electromagnetism, covariant derivative seems to be a mathematical construct to preserve gauge invariance. How do we interpret it physically in flat space-time? I mean, we have to say that the fiber space in some sense is as real as the space-time on which the fiber space is defined. So it's not just a mathematical construct. Gauge invariance is also required to derive conservation of a charge. Your question is good. How do we interpret it physically in flat space time? Conservation of charge, and we should give some reality to the fiber space. That's what I can think of. It's not just a mathematical construct. And there's also, this Bohm-Aronoff effect, which testifies to the realistic nature of the vector potential. But a good question. Maybe we take it up again in the evening or on Saturday. So under a displacement delta x mu from a point x mu, the parallel transport of psi x picks up a phase. What this means, what I mean by this, that I make this transformation, gauge transformation on psi. When I look at del mu psi, it is picking up this extra component. Apart from the normal transport, I am picking up this extra component. Okay, and this bit is actually the same as the change in A. So the change in A, delta A was related to the del mu theta by this relation. So this is the change that is happening in psi. This is the change that is happening in psi here. That change is given in terms of A because of this relation. Del mu theta is the change in A. So every time you move psi to a neighboring point, you pick up this extra bit. This is what the connection does, right? The connection is needed. You need to make this much change so that your psi transforms. This is parallel transport. Okay, I mean, if you want to compare vectors at neighboring points, take into account the change that has come because of this issue, then you have to make your psi will change like this. Psi x plus delta x is psi of x minus delta x mu d mu psi. This object, okay, maybe this is quick. The change in psi is given here. And this is the change in psi, and you can write that change in psi in terms of A mu or equivalently in terms of d mu. Okay. The change in psi as you go from one place to another is given by this. I was trying to see if I can say this nicely. Okay, I'll leave this for now. It's contained in this equation. Okay, please accept this for the moment. Psi x plus delta x is psi of x minus delta x mu d mu psi. This is what, suppose I make the following 4 changes now. Transport the field around a closed loop in the mu nu plane like we do for Riemann tensors. Start at some point in space-time, go like this, go up, back, and come back down. So there are these 4 changes. Move delta x mu along mu direction, then perpendicular delta x mu along nu, back minus delta x mu, then back minus delta x mu, a closed square. Every time you do that, this change happens. Psi, first movement to the right along delta x mu, you get this change in psi. Then once more. I have not proved this in detail. If you will find that this sends psi to you simplify all this, keep only up to the second order, you will get this commutator in D arising, because there are d nu commutator. This is d nu minus d nu, and that is this object. This quantity can be shown to be proportional to the field tensor. I didn't do this nicely in detail, but do you get some hang of what's going on here? You want to ask something? Yeah, so what is happening? The connection A is different at different places. A mu of x is not the same everywhere. So if the connection itself is changing, I get curvature. If A was a constant, my field tensor will be 0. Then there will be no curvature. Because A has gradient, the field tensor is non-zero, and the A is controlling the change in psi when I move it from one point to another. But A here is different from A here. So when I bring psi back to the starting point, when I come back to the starting point, I don't have psi, I have a change in psi which is given by this relation. I did not explain this properly, but I hope you get some hang of why this is like the Riemann tensor case. So A is like gamma. The vector potential is like the connection, Christoffel symbols. The field tensor is like the Riemann tensor. Again, there is something curious here. A is the potential. The corresponding thing would be g mu nu in gravity. But g mu nu is not the connection. G mu nu is the potential. In electrodynamics, the potential is the connection. In gravity, the force, the gravitational force is the connection. Gammas are gravitational forces, right? Derivatives of the metric. Gammas are So in electrodynamics, the connection is the potential. In gravity, the connection is the derivative of the potential, the gammas. In electrodynamics, the curvature is the field tensor. In gravity, the curvature, the Riemann tensor, is the second derivative of the potential. In electrodynamics, the curvature is the first derivative of the connection and of the potential. In gravity, the curvature is the second derivative. So there are differences, but there are also similarities. So that becomes very interesting when you start trying to think of unification, that why this difference is there despite the similarity.
Also in gravity, the connections are not tensor.
Yeah, the connection not tensors because of the equivalence principle, yes.
Here it is tensor. It's a vector.
Yes, the connection is a vector. In gravity, the connections, the symmetric part is not a tensor. That is true. I agree.
Can you suggest any textbooks where this kind of discussion is?
Yeah, okay. We have to look at books like Differential Geometry, Gauge Theories and Gravity. And that's that title, if you look, I think there's a Japanese author, which is where I saw these things. Nakahara, I will look, I'll tell you the exact name. Yeah, so we need to look at books like Differential Geometry, Gauge Theories and Gravitation, where these things are discussed, the commonality between gravity and gauge forces in the language of connection and curvature. Okay, it's time. Anyway, so give me 2 minutes. This is just a review for what we'll start from tomorrow. So what's the fiber bundle for Maxwell's electrodynamics? The gauge field is a connection on the U1 principal bundle. Name of the book is a Japanese book. I will tell you tomorrow. Differential Geometry, Gauge Theories and Gravitation. That's roughly the name of differential geometries, gauge theories and gravitation. Okay, so what is the fiber bundle for Maxwell's electrodynamics? On every fiber bundle, I will need a connection which will tell me how to transport vectors and tensors from one point to the other, so that the differentiation obeys the gauge invariance. The gauge field A mu is a connection on this U1 principal bundle. The field strength is the curvature of that connection. We will subsequently understand gravitational field as connection on the tangent bundle. The Riemann tensor will be the curvature of the associated connection. For electrodynamics as well as for gravitation, there is a Bianchi identity which is interpreted as the boundary of a boundary is 0. This is for tomorrow onwards. For electrodynamics, the Bianchi identity gives the source-free Maxwell's equation, something known as the exterior derivative acting on the curvature 2 form is 0. This star is a so-called, we will do this tomorrow, Hodge star duality operator, exterior derivative acting on d star f. These are Maxwell's equations. Source-free Maxwell equations are the same thing as this so-called Bianchi identity. The action principle for electrodynamics will be written in this nice way using this so-called wedge product. And just lastly, to summarize, Maxwell electrodynamics versus gravitation, the last slide. The base manifold is space-time, for gravity also. Fiber is the Lie group U1 structure group. Fiber is the tangent space Tp of M. There is no tetrad, there is no metric. And the structure group on the fiber is SO13, here it is U1. There is no tetrad in electrodynamics. Tetrads EA define tangent space in the gravitational case. The gauge field A is the connection. The gravitational field is the spin connection on the tangent bundle. Think of this as Christoffel symbols, gammas. It's the same information in the spin connection. So here, the gauge field A is the connection. Here, the gravitational force is the connection. The field tensor F is the curvature. The Riemann tensor, the tidal tensor, second derivative of the metric, is the curvature of this connection. Bianchi identity holds in both cases. The so-called boundary of a boundary is 0. Field equations are derivatives of curvature. Right, field equations involve F mu nu derivatives, curvature derivatives. Here, field equations involve only curvature. Because Riemann tensor is the curvature, Einstein equations are just Riemann tensor. They are not involving derivatives of Riemann tensor, right? Einstein equations don't have derivatives of curvature. Maxwell's equations have derivatives of curvature. Bianchi identity has derivatives of curvature, and in the electromagnetic case, the so-called Bianchi identity does have derivatives. The field, right. Interestingly, so this is the Bianchi identity, we will see that tomorrow, and that does involve derivative of curvature in both cases, but in the electromagnetic case, that is one of the field equations. In the gravitational case, the Bianchi identity is not a field equation. So I just wanted to give you a feel for the similarities and differences, which tells you that something very interesting is going on. When things have similarities, we need to look deeper as to why the differences arise. Is there a deeper layer where the differences go away? So I have some thoughts on that. Maybe you can talk in private. We'll stop now. Thank you very much.